Good morning, everybody. Hope you're all healthy and safe at home. We are going on to the last section of our third module, that is section 9.17. In this section, we shall be discussing about the change of variables in multiple integrals. So, we are familiar with the changing of variables. Like if you are given the double integral, or if you are given any line integral, we usually or mostly solve that particular integration with the help of method of substitution, right? So if we have a function in terms of x, what we do is we modify it or we change it to our convenience by substituting this x is equal to some other function in terms of u, say g of u, and correspondingly what happens is the limit of the integration will also change with respect to u, and our d of x will be replaced by du. So that is in line integrals or in simple integration, we are familiar with the concept of substitution, and that is same as changing variables, and that was the case of line integrals. And when we came into the picture of double integrals, what we did was there was a possibility of interchanging, like if the integral was dx dy, then sometimes in some cases the problem was easier to solve if we had converted into dy dx, right? We have done such problems also. So that is another type of changing of variables. And also we had discussed about the polar coordinates, right? We had converted dx dy into r dr d theta, right? Because in some cases the surface when it is projected onto the xy plane, it will form a circle, a part of a circle, and whenever we are having a circle or a part of circle or expressions of the form x square plus y square and all in our integration, it was very convenient to use the polar form. So these were the things that we have so far encountered, like changing of variables. Now the change in case of multiple integrals, it is till now we have learned triple integrals so far. So in case of triple integrals or double integrals, it is not actually as simple as the case of our line integral, simple normal integration. That is in individual integration, or suppose we have to change the variable x or replace it by u, then we know x is equal to some function of u, and if given the value of x, we can find the limits of theta. So that was much easier. But in case of multiple integrals, when we move on to multiple integrals, the integration process becomes more difficult, and also the finding the limits also becomes a little bit more difficult. So in this lecture we shall be discussing about such type of integration. So we are familiar with the changing into polar form. Similarly we shall be using a different component which will help us to evaluate the multiple integral or change in variables. So before that we shall see an example which shall depict the change or the change in the image of the region that is given to us. So let's see example 1. Okay, so the example is as follows, that is we are asked to find the image of the region S, which is shown in this figure 9.17.2a. Okay, this is our region. The cream colored portion, cream shaded portion is our region, and we have to find the image of the region S under the transformation x equal to u square plus v square and y is equal to u square minus v square. So I had mentioned, now let me explain what is this transformation. It is nothing much. I am transforming the variable x to u or v in terms of u and v. So that is, that particular expression is called as the transformation. So here the example is to find the image of the region S under these transformations. That is given the region S, what we are doing is I am splitting it into three portions, like S1, S2 and S3. Okay, S1 is just the line v is equal to 0. S2 is the curve u square plus v square equal to 4, and S3 is the curve u square minus v square equal to 1. Okay, and the points are given, plotted in the figure. Now we have to find the image of this region under this transformation. What will happen when we apply this transformation, right? So first let's see on S1. On S1 v is 0, right? So if v is 0, what I'm going to do is I'm going to substitute it in x and y. What will be x? X will be u square, y will also be u square, so x is equal to y. So y equal to x will be the image of corresponding to S1, that is the straight line y equal to x. Now from where to where? S1 is moving from 1, 0 to 2, 0, right? So u is 1 and v is 0, u is 2 and v is 0. So here x becomes, when we apply 1, 0, x becomes 1, and what will become y? Y will also become 1, and when we reach 2, 0, x and y both becomes 4. So we are moving from 1, 1 to 4, 4 along the straight line y equal to x. So that is the image of the portion S1. So I hope it's clear. Okay, from 1, 1 to 4, 4, y equal to x. Now let's see what happens on S2. On S2, what happens is, it is given to us u square plus v square is 4, right? So if u square plus v square is 4, our transformation is x is equal to u square plus v square. So this implies x is 4. So it is a line, x is equal to 4. It is a horizontal, it is a vertical line, x is equal to 4. Now we shall see what will be the change in y. So in S2 you can see that the point is moving from 2, 0 to, we have another point given to us, that is root 5 by 2, root 3 by 2, right? So when we apply that, what will be y? Y transformation is given by u square minus v square. So when we are at the point 2, 0, u square minus v square will become 4, and at the point root 5 by 2, root 3 by 2, y will become root 5 by 2 whole square minus root 3 by 2 whole square, which is nothing but equal to 1. So y is actually moving from, when on S2, when we move from 2, 0 to root 5 by 2, root 3 by 2 to that point, y moves from 4 to 1, that is it moves downward along the line segment x is equal to 4. So S2 will be nothing but, the image of S2 will be a vertical line x equal to 4 moving downwards. The direction is from 4 to 1. Okay, I hope it's clear. Now let's move on to S3. In case of S3, we are given u square minus v square equal to 1. So by the transformation we get y equal to 1. Okay, now we shall see the variation in x. So as we move from the point root 5 by 2 to root 3 by 2 to 1, 0, the equation will be x moves from 4 to 1. So it will be, the image of S3 will not be none other than a horizontal line y equal to 1 moving from 4, 1 to 1, 1. So according to the orientation or the direction which is given in the figure, we are making the necessary arrangements. So the image of the region S is nothing but this triangular region along the under the transformation which is given to us. Okay, so you can see the figure has become a bit more easier to evaluate the area. If you are asked the area and all, we are very much familiar with the area of a rectangle, of a triangle. So in some cases, when we apply these transformations, the valuation of the integration becomes a little bit more easier. So that is how we can define or determine the image of any region given to us by just transforming it into the corresponding forms or under the given transformation. Now to evaluate the double integrals, we have to introduce another terminology which is called the Jacobian determinant. Okay, so the corresponding the Jacobian determinant is as follows. It is simple. Given that the transformation is x is equal to f of u comma v and y equal to g of u comma v. These are the two transformations of x and y. Then the Jacobian determinant is given by dou of x comma y by dou u comma v. Okay, and what is this value? This is nothing but the determinant of dou x by dou u, dou x by dou v, dou y by dou u, dou y by dou v. So don't forget this. This is important. The Jacobian determinant is given by the determinant of dou x by dou u, dou x by dou v, dou y by dou u, and dou y by dou v. Okay, this is corresponding to the transformation x is equal to f of u comma v and y is equal to g of u comma v. So if the transformation is basically a function, right? X is a function of u and v. So if this function is 1 1 and on 2, then their inverse will also exist. And those transformations will be 1 1 and on 2 because we are transforming it, right? So the function we can also form inverse transformations, and that will be like u in terms of x and y and v in terms of x and y. So in that case, the Jacobian will be given if u is equal to h of x comma y and v equal to k of x comma y. Then the Jacobian is given by dou u comma v by dou x y. This is the notation, okay? The notation of the Jacobian. It is actually the determinant of dou u by dou x, dou u by dou y, dou v by dou x, and dou v by dou y. Okay, dou u by, like this, it is going like this. I'll explain it here. Dou x by dou u, dou x by dou v, and dou y by dou u, and dou y by dou v. It's simple to remember. Okay, and there is one thing that you must know, that is the product of these two Jacobians, that is of the corresponding transformation and its inverse, will be equal to 1. Okay, so this is the Jacobian determinant. Now there is a example to determine the Jacobian which is given in your textbook. It is easy. Determine the Jacobian of the transformation x is equal to r cos theta and y is equal to r sin theta. So we have to find dou of x comma y divided by dou of r comma theta. Okay, x is a function in terms of r and theta, right? So it will be dou of x comma y by dou of r comma theta. Now if we evaluate it, it is simple. What will be dou x by dou r? It will be cos theta, and dou x by dou theta will be minus r sin theta, and similarly dou y by dou r is sin theta, and dou y by dou theta is r cos theta. So altogether the determinant value will be r cos square theta plus sin square theta, which is equal to r. Okay, so that is how we can determine the Jacobian of the given transformation. So keep this in mind. Now with the help of this Jacobian, we have a theorem, or we will be able to evaluate the double integral as follows. That is, if f is continuous in the region, that is important because the partial derivatives and all must be existing. So if f is continuous in the region R, then double integral over R f of xy dA can be replaced as double integral over S. That is, R is the region given to us, S is the region which is formed after the transformation. F of, instead of x we have f of u comma v comma g of u comma v, and into the Jacobian into d of a dash. d a dash is nothing but the transformation du dv. Okay, dA is dx dy and dA dash is du dv. So this is how the transformation works out. So this term, this Jacobian, actually it comes by, if you just recall, when we make the substitution like x is equal to u square, or x square is equal to u in the normal integration. Okay, if we make x square is equal to u, then for us 2x into dx is equal to du. So dx is nothing but du by 2x, right? So there is another term involved there. Du is not equal to dx all the time. So that is how dA has been changed to the Jacobian of x and y into dA dash. Okay, so this is how we can evaluate the multiple integral, or bring in the change of variables of the corresponding multiple integrals. So that is a theorem. We are not going for the proof of that theorem and all. So we shall see how we can use it to solve the corresponding double integrals. So let's see example 3. Now we are asked to evaluate double integral over R sine x plus 2y cos x minus 2y into dA over the region which is given in figure 9.17.4a. So this is the region, R is the region. Okay, so what we have doing is, again we have to evaluate this, and we are going to first we will form the image of this region corresponding to the transformation. Now what will be the transformation here? Clearly this integration becomes difficult because of the fact that it's not simply sine x into cos x or sine x into cos y. It is sine of x plus 2y into cos of x minus 2y. So we replace this x plus 2y and x minus 2y. So put u is equal to x plus 2y and v is equal to x minus 2y. And now let's see what will be the corresponding mapping or the region in order to obtain the limits. Okay, we have to change this R to S, right? So we have to form the image of this region according to this transformation, like we have done in the previous example, in order to find the limits. So first S1 is a portion where y is 0. So if y is 0, u will be equal to x, v will be equal to x. So again a straight line, v equal to u. Okay, and there is a variation from 0, 0 to 2 pi, 0. So the corresponding transformation will be from 2 pi to 2 pi to 0, 0. As we move from, we are moving from 2 pi, 0 to 0, 0, right? So the transformation will be from 2 pi to 0, 0. I hope this much is clear. So this is a line segment v equal to u. Now S2 is a line segment corresponding to x equal to 0. So if x is 0, we have u is equal to 2y and v is equal to minus 2y, right? So u is equal to minus v. So this is the line segment which will form downwards. Now the movement, from where is it moving? We are moving from 0, 0 to 0, pi. So we'll have to move from 0, 0 to 2 pi, minus 2 pi, right? U is 2 into pi, that is 2 pi, and v will be minus 2 into pi, that is minus 2 pi. So the line segment will be v equal to minus u from 0, 0 to 2 pi, minus 2 pi. Now let's see what is S3 corresponding to S3. Corresponding to S3, we have x plus 2 pi is x plus 2y is equal to 2 pi. That is nothing but u is equal to 2 pi, right? So u is equal to 2 pi. Now we have to see the variation of v, right? V is x minus 2y and it is moving from 0, pi to 2 pi, 0. So when x is 0, we have x is 0 and y is pi, we have v moves from the point v will be 0 minus 2 pi, that is minus 2 pi. And when x is 2 pi and y is 0, we have v is 2 pi. So it moves from minus 2 pi to 2 pi, right? So we have the vertical segment u is equal to 2 pi and it will be like moving from 2 pi to 2 pi, minus 2 pi to 2 pi, 2 pi, right? From 0, pi to 2 pi, 0 means 2 pi, minus 2 pi to 2 pi, 2 pi. So I hope the image of the region is clear in your mind. Now with the help of this Jacobian, we are going to evaluate the double integral. So for that we have to find dou, by the formula we have to find dou of x, y by dou of u, v, right? So here we have u is equal to x plus 2y and v is equal to x minus 2y. So what will be the value of x? X will be, we have to determine the value of x and y in terms of u and v, right? So x is equal to 1 by 2 u plus v and y is equal to 1 by 4 u minus v. Just solving those two equations, we can easily get the value of x and y. Now what will be dou of x, y divided by dou of u, v? That will be equal to dou x by dou u, that is 1 by 2, dou x by dou v, again 1 by 2, dou y by dou u, that is 1 by 4 and minus 1 by 4, and the determinant of that is minus 1 by 4. So this is how we are going to determine the double integral over R. This is equal to double integral over S sine x plus 2y is u, x minus 2y is v, sine u cos v into the Jacobian, that is minus of 1 by 4 modulus. into dA dash. Here dA dash is nothing but dV, du or du dV, whatever it is. So here we have the variation. U is a line segment, and here u varies from 0 to 2 pi and v varies from minus u to u. Okay, you can see in this figure we have this variation. V is moving from, if you draw a line segment in this point, pointing an arrow upward, we have v varies from minus u to u, and u is actually varying from 0 to 2 pi. So if we move that line segment along 0 to 2 pi from minus u to u, we get this shaded region. Okay, from this figure itself, it is clear the variation of u and v. So the integral will become much more simple because it is sine u is constant. So we have sine v, so that is varying from minus u to u, so that is sine square of u, and 1 by 2 into 0 to 2 pi sine square u. Sine square u, we can convert it 1 minus cos 2u into du, that is solving we get the answer is equal to pi by 2. Now this is simple to evaluate when we have made the substitution. If it was of this form, it wouldn't have been as easy as this evaluation of the integral. Okay, now we shall see just one more example which is given in your textbook. So in the previous example, what was it, that the integrand was a bit complicated, that is we had sine x plus 2y cos x minus 2y and all. Now here what is it is, we are asked to evaluate double integral over r xy into dA over the region which is given to us. Okay, here integrand is simple, it's just xy, so it is simple, but the region is a bit complicated. It is formed by the intersection of the parabolas y is equal to 4x square, y equal to x square, and the curves xy equal to 5, xy equal to 1 and all. So here the problem is with the region. So what we are going to do is, we are going to make the substitution corresponding to the curves that is given to us. That is, we are going to make u is equal to y by x square, okay, with the help of this using y equal to x square and y is equal to 4x square. We are using u is equal to y by x square and v is given by xy. So what is the use, or what is the use of making this transformation? With the help of this, the variation of u and v will be easy. Why? Because in one case, when y is equal to x square in this curve, when y is x square, u is 1. When y is 4x square, u is 4. So u varies from 1 to 4 and v varies from 1 to 5. So that is the variation. So we actually, the S region, S image of this region will be much easy, because it will be actually a rectangular region in which u varies from 1 to 4 and v varies from 1 to 5. So this complicated region becomes into this simple region. Okay, so now we can determine the double integral once we know the limits. Now in this case, what we are doing is, we have to determine the value of dou xy by dou uy. So here I am going to make use of the note that dou xy by dou uv, dou u comma v into dou u comma v by dou x comma y is equal to 1. The transformation and its corresponding inverse. So you can do it directly also, but this is also another method of doing it. Okay, so this will be from this, it will be difficult to determine x and y in terms of y and x and y in terms of u and v, right? So that's why we are going to use this u and v itself. We are using the inverse transformation and finding the value of the Jacobian. So here you can, as I mentioned earlier, you can find the value of x and y in terms of u and v and determine the Jacobian individually. Both the value will be same. So here dou u comma v by dou of x comma y will be nothing but dou u by dou x. What will be dou u by dou x? It will be minus 2 by x cube into y, and dou u by dou y will be 1 by x square. Now what will be dou u by dou v by dou x, that is y, and dou v by dou y will be x. So here it was easier, much more comparatively it is easier to determine the partial derivatives instead of transforming it into functions of u and v. Okay, so this determinant is equal to minus 3y by x square. So by the formula we can determine what will be the Jacobian dou of xy by dou u comma v, which is 1 divided by dou of u comma v by dou of x comma y. Okay, so that will be nothing but minus x square by 3y. Now what is y by x square was u, so x square by y will be nothing but 1 by u. Okay, so this is equal to minus 1 by 3u. So what will be our integral over our xy dA? Xy was the substitution was made by v. Double integral over s, v into Jacobian minus 1 by 3u into dA dash, dA is dv du. V varies from 1 to 5 and u varies from 1 to 4. So the integration has become very simple. You can easily solve this and the value comes out to be 4 log 4. Okay. So see how the transformation has made the valuation of the integral much more easier, and in this case also the region, the little bit time consuming portion is in determining the corresponding image of the region given to us. So but that is it is not much difficult also, and there is one more problem, that is you have to understand what transformation you have to make. Okay. That is kind of similar to the what substitution must be made to the integral, which we have done in our earlier classes also, right? What must be the value substituted so as to make this integration much more easier. Now we have the same concept in triple integral also. Okay, we have the Jacobian. The Jacobian is as follows. Just keep in mind the transformation is x equal to f of u comma v comma w, y is g of u comma v comma w, and z is h of u comma v comma w. Then the double integral over d, f of x y z dv will be nothing but non-double integral, triple integral. Triple integral over e, f of we replace x y z by f g and h, and the Jacobian and dv dash. Now what will be the Jacobian? Jacobian will be dou x by dou u, dou x by dou v, dou x by dou w. The next row will be dou y by dou u, dou y by dou v, dou y by dou w. And the third one dou z by dou u, dou z by dou v, and dou z by dou w. You have to determine the determinant of this value. So that is how we can evaluate the corresponding double integral. So we use the Jacobian, which we have learned, to evaluate this corresponding double integral in a much more easier manner once the image of the region has been determined successfully. So that's it for today's session. Thank you. Stay home and stay safe.